All right, I don't think anybody else is coming. I'll get started. All right, well, welcome everyone. I'm going to talk about CMake and the state of C++ 20 modules. So at this conference, a lot of people have been coming up to me and like, oh, hey, yeah, Bill Hoffman, yeah, I think I know you. You're the CMake guy. But outside of work and stuff like that, like in other communities, I'm the sandal guy. Running down mountains and crazy stuff. I'm also the a Kitware guy, one of the founders of Kitware. A little bit about me. From 1990 to about 99, I was at GE Research in a computer vision group. Helped them move off of Symbolics Lisp machines to C++ on Solaris Spark workstations, and later Linux and Windows. I was sort of the build guy, the library guy, helping them to design their stuff. And C++ was all shiny and new back then, and we were all trying to figure out how it all worked. Did a lot of stuff with CMake and Auto Tools. And in 98, I helped start Kitware. And I've done lots of development in CMake, the Insight Toolkit and the Visualization Toolkit. Mostly the pointy-haired boss guy now, looking for funding for guys to do exciting work on CMake and other projects at Kitware. But certainly, CMake is a community effort. We've had 971 contributors. It's probably more now. And I would say Brad King and Ben Bakel are really the CMake guys these days. And there's, the book not written by us, by Craig Scott, which is a fantastic book on modern CMake and professional CMake. So it's really growing into something beyond what it started off at. Quick thing on Kitware, we're a company built completely on open source software. We do computer vision, data analytics, scientific computing, medical computing, and software solutions. Quick history of where CMake came from. Kitware was the lead engineer team for the Insight Segmentation Registration Toolkit. If you look at itk.org, this was funded by the National Library of Medicine, part of the Visible Human Project, and they wanted to create this code that would, in C++, that would codify the state-of-the-art in segmentation and registration. And Kitware was one of the commercial companies on the project. We were tasked with making it work on Unix, Windows, and Mac. And like I said, I had this history of a build system, and I really wanted to make something that would work on all these systems in the same way, but also allow developers to use the tools on those machines. So I've always been sort of a tooling person. I hate seeing people waste time on things that aren't their actual work. So testing software is really important to me, and we were doing continuous integration testing before it was really popular back there in the early 2000s. And we've grown the project since then, obviously. And we adapt to new technologies so the developers don't have to. So if a new IDE or compiler comes out, CMake will have it. So if you're already using CMake, you get that port for free. One of the biggest examples of this was the Ninja command line build tool from Google. The support got contributed to CMake as Ninja matured. I think probably 3 months after Ninja came out, there was a Ninja generator in CMake, and suddenly anybody that was using CMake had this new powerful, more parallel build tool. When Apple Silicon came out, the build stuff worked pretty quick. And now we're working on C++ 20 modules. That has been a little bit of a slower story, but I'll get into why that takes so long. First, a little background on running CMake. It's important to sort of understand this, and to understanding this helps you understand what makes adding modules into CMake build system a little more difficult. So the way CMake works, you run CMake, it reads this CMake cache file if there's one present, and that stores sort of the state of variables. It's kind of like environment variables. Back in my GE days, a lot of build systems had, source this bunch of environment variables, then type make. And if you didn't source those variables or they were wrong, things could get written all over your disk and make a big mess. So I wanted to not use environment variables in CMake and have them in one file that went along with the build tree. So once you configured it and all those variables are set, they don't change unless you specifically go in and edit them, but you've got everything stored in one place. And then you can iterate on that with the CMake GUI, and then once it's ready to actually do the generation, you generate the build system. And that could be Visual Studio project files, MS Build, or it could be Ninja files, or it could be Make files, or something else in the future. And the point is, CMake's not running anymore. Right now, I've turned it over to the build system of choice, and CMake's not actually running anymore. So we don't have control over everything that has to be done through that build system. So keep that in your mind. Okay, so modern CMake. So originally, CMake had a structure much like the old AutoTools make files, where as you cascaded down directories, the include paths would filter down. In modern CMake, the target, which could be an executable or a library, is the source of the information, and you put things like include flags, for example, on a target, and then each target needs to fully describe how to properly use it and how to build itself. And there should be no difference between external and internal targets. By external targets, I mean something built with some other build system, or CMake in another round of builds, or something you found in a Debian package or RPM package. CMake should be able to consume that, and then it should look like something in the CMake code, like something you built locally. So there should be no, ideally, distinguishing between external and internal targets. And that's sort of the key of modern CMake. This idea that you don't flow down through directories. The directory structure can look any way it likes, but what really matters is the dependencies between these targets. So if library B depends on library A, and you link in library B to this executable, it's going to pull in library A and get all that transitive dependency stuff working, and all those flags that come along with it. And you do this by giving usage requirements. You can do private ones, which are only during the build of yourself, interface things, which only consuming targets use, and public is sort of private and interface. And then you can use what's called generator expressions to specify, a build interface or an install interface to a library. And that generator expressions, going back to that first slide that shows sort of how CMake works, that's important because as its generator expressions are expanded when the actual build system gets written out. Or like during the install phase, so when it needs to know these things, not necessarily at the time when it's evaluating the CMake code that the user's writing. It doesn't have the answer yet. If it's writing out to a multi-config, like Ninja multi-config that does debug, release at the same time, those are going to have potentially different values in each of those variants. So you need to have some way of expressing values that get evaluated at that point when you actually get down to a concrete instance. CMake also has a full cross-platform install system. You can specify the rules to run at install time. You can install targets, files, directories, and provide default install locations. And again, so I'm going to be talking about C++ named modules. How many people went to Daniel's talk yesterday? Yeah. Most of you, good. So we're not going to be talking about header units, and maybe we'll never have to if we have our way. All right, so I thought I'd have fun with ChatGPT. Hey, does CMake support C++ 20 modules? Yes, apparently, since 3.21. And then wrote some code on
how to do it. That's completely useless. I think it found some example of someone trying to get it working before there was any support or anything, but it's kind of funny. But maybe in a few years it'll get this right when the implementation's actually there. Okay, so one of the concepts is the BMI, or Built Module Interface. There's a paper on this. And the idea there is this is the compiled version of a module that's consumed essentially like the sort of like a precompiled header file, but a little bit different, and different from an object file. MSVC has a .ifc file, GCC has a .gcm file, and Clang has a .pcm file. And these files are a little more touchy than an object file, so they don't have ABI compatibility, but they have BMI compatibility, which is something we really don't completely understand yet, and there needs to be some work there. But the point is, this built module interface comes as a side effect of compiling something that exports a module in C++20. So let's look at a really simple example. I've got b.cpp, a.cpp. A exports module A and imports B. B exports module B. And if I just try to compile a.cpp on the command line, oops, it fails because it couldn't find module B. So this is something completely new to C++, because if I go and change it a little bit and I compile B first and then compile A, everything is fine. So build order suddenly matters in C++ with modules. So this makes things much more complicated and presents the classic chicken and the egg problem, because modules require the build system to know which files produce which BMI files and which files consume them. And we, of course, need to parse/compile a file to find out that information. So we need to compile the code before we can compile the code. Okay, so CMake does have some experience with modules, Fortran ones. In 2005, we added the initial support for makefiles. We added support into Ninja in 2015 to do this dynamic dependency, because remember, CMake's not running when the build is happening. Ninja's running. So we have to teach Ninja to be able to dynamically create this graph. And it didn't know how to do that. And the Ninja folks were like, what are you guys doing? Who cares about Fortran? What is this crazy stuff? So despite working with them, they had very low interest in actually upstreaming it, so we had to fork Ninja. And then C++ modules came around, and then suddenly they got interested in this support. But fortunately, we already had it, and it was in pretty good shape. So 4 years later, they finally merged the change because of C++ modules. So that's the reference in the Ninja manual for dynamic dependencies. And this allows for dependency information to be dynamically discovered from the source file content during the build in order to order the build correctly. So this is unlike header dependencies, which are only needed on the second run or later to rebuild correctly. So the first time you're building on a completely new tree, before you just needed to build all the object files. It made no difference what order they were in, and you could just do it all in parallel. And as you were doing that, you could build up the header file dependency information, and you didn't need that dependency information until the build, until after you built everything for doing incremental builds. But now, actually, during the build, we're going to be discovering this tree of dependencies. So how does CMake do it? It has a Fortran parser based off of this program called MakeDep F90. We can
will not do this for C++. And we also did patches to Ninja build tool, which is now upstreamed, and then the dynamic dependency collator inside CMake. So as C++ 20 modules were going around through the standards committee, Ben and Brad wrote a paper describing how CMake supports Fortran modules and its applicability to C++. And this eventually led to a paper describing a format for those dependencies. The P169A9R5 paper defining this format. It's a JSON file that compilers can use to give you imports and exports, and essentially to define that who produces what and who consumes what. So the way this all works is you have each source file gets scanned and produce a dynamic dependency information, and then you collate that all together for the target, and you have the dependencies, and then you can build things in the right order. The quick overview of this process: CMake runs, that generates the build files, a dependency JSON file per target. Then Ninja runs, and that causes the C++ compiler to scan each of the translation units and get one of these P116A9R5 file JSON files. And then once that's done, CMake runs the dynamic dependency on each target. You get a cxx.dd, which is the Ninja dyndept file, a tu modmap file, which is passed to the compilers, paths to the BMI, and then this CXX modules JSON, which is a CMake readable version of cxx.dd. And then we're finally ready to compile them in order based on the dynamic dependencies and create our .os, .libs, .exes, etc. Yes?
So the cxx.dd is the thing that tells basically Ninja what order things have to be built in, and then the mod map is what tells the compiler where to find the BMIs? Is
yes.
That correct? Okay.
That's correct. So the question was, well, I guess get the microphones now. So where are we today? Happy to report that support for the P16A9R5 is in compiler releases. Visual Studio 2022 previews have it, and Clang 16 has it, which was a big one. GCC still has a patch for name modules, and we are working diligently again on getting that patch upstream. There was I think it broke a few tests, and we're working on fixing them and getting that in. Hopefully that gets in soon before the next release of GCC. CMake 3.26 or newer has experimental support. This is turned on by setting the CMake experimental CXX module CMake API token. And once, I'll get to that, but that's essentially how you get it right now. Visual Studio 2022 has a scan dependencies option. Clang 16, the module dependency stuff is put into Clang scan deps, and it's in Clang 16. And you can see that it supports a P1689, generate standard C++ module dependency format. The CMake generators that are supported currently are Ninja. We haven't done the make files. And then Visual Studio 17 2022, aka MS Build, supports this. And they're actually using the same technique we're doing, using their own scan dependencies. And basically repeated what Ninja does in CMake. So some C++ Now success stories to me, and why this conference is great and important for moving things like this forward a little bit faster. So last year this time, there was a big discussion. Daniel was working away on his laptop. I think he even managed to get Windows compiler on his laptop, and we were having trouble with internal modules and the way those partitions worked, and Visual Studio's interpretation of the standard. And we went back and forth, and eventually
came up with a solution, and now the cases are fixed, and we don't have to. What this would have meant is if you had module partitions in some cases, you would have had to mark that extra property in your CMake files, as opposed to allowing the compiler to discover it when it's doing the scanning. So thanks to Daniel, Brett Brown, Ben Bakel, Brad King at Bloomberg, and the folks at Microsoft. It was a combined effort to get this done, but I think this conference really helped speed things up. And then hot off the presses, as I was preparing for this talk, I started playing around with the examples, which I'll get to a little bit later in CMake. And I was trying the Visual Studio MS Build generator on the internal partition one, and it failed. And I was like, wait a minute, I thought they said they were going to fix that like a while ago. And then it turns out we had turned it off in our continuous integration testing because it wasn't working in some version. I'm like, we should probably ping them and see what happened. And sure enough, they did implement it, but it required a small change to CMake. Basically, we had to say, so if we were saying, right now we were saying compile as module, and they treat that as their way of doing things with the modules. Instead, we had to change it to compile as just CPP, and then when they do that, because they didn't want to override compile as module, because that would have been a breaking change, which makes sense. So we just had to change the code in CMake to generate the new flag, and now there's it should be in the next version of CMake, and it will support that. So, and that came from me playing around. I think they've had it in there for a while. They just never let us know when they implemented it. And we weren't looking actively. All right. Slight sidebar, an improvement from last year when I had just gotten a Mac. And now this is like the perfect CMake developer machine with parallels. I'm able to run Visual Studio, ARM and x86, and I'm also able to have Clang and GCC working, so I can test all the major platforms on one laptop. And so just a slight sidebar, kind of cool developer setup you can do with a Mac. Okay, now back to that a.cpp. Let's run it through the scan dependencies, and you can see that at primary output is a.object, outputs a.json and a.ifc file, and it provides module A, and it gives the source path to a.cpp, and it requires B. And if we go back to B, we can see our primary output is b.obj. We got a b.json and an ifc, the BMI file, and we provide B, and there's the path to the source to B, and we don't require anything. Okay, so CMake has a relatively new feature called a file set, which is important to understand how CMake modules are handled. And that is through the target sources. You can do file set and give it, right now, originally it only had headers. So if we look at an example of a header-only library implemented with file set, we create this library called eigen. It's an interface library. We do target sources, eigen interface, file set headers, base star source files, and I'll list a few of the eigen.h files. And then I can say install target eigen export, file set headers, destination include eigen. I can install the namespace upstream : destination lib CMake eigen. I can add an executable. I can link that executable to eigen. And then if I run CMake install prefix, I'll give it a directory. I do the build, and then I do install, and you can see it's installing the into this install directory, include eigen, and it's all nicer. And before, this was a lot more complicated to do before file sets.
But these become important for modules as well. Really important for modules. So we added another type, which is beyond the headers, which is CXX modules. So if we go back to our A.cxx, B.cxx, we'll create a library, simple library, and we'll give it a file set, CXX modules, A.cpp and B.cpp. We run CMake -g ninja. We get configure, we get a warning that this is experimental. Generating build files are here. And then we can do ninja -v. And you can see it does scan dependencies on A, does scan dependencies on B. And then we're running, where are we? Yeah, the collation. I'm having trouble seeing it. Yeah, there it is. The CMake -v dynamp. That's the collation step. And then it goes through and compiles them in the correct order and builds the library in the executable. And we can do the same thing with G++. And the same thing with Clang now. And with MS Build, and they're doing the correct order as well. So I thought what would be useful to get across how this all works is to sort of walk through the new additions to the CMake documentation as relevant to C++ modules. So again, we talked about file sets. There are C++ modules, sources which contain C++ interface module or partition units, essentially, i.e. those using the export keyword. And this file set may not have an interface scope except for imported targets. We also have module header units, which doesn't really do much right now, but the install command also has some new stuff on the CXX modules BMI. And any module files from C++ modules from public sources and a file set of type CXX modules will be installed to the given destination. All modules are placed directly in the destination directory, as no directory structure is derived from the names of the modules. An empty destination may be used to express installing these files. So essentially, this is how you install your BMI files. There's a new property on targets, CMake CXX scan for modules. And this basically is a performance idea. So if you had, say, maybe one or two libraries that use modules but had a larger code base and didn't want to pay for this upfront scanning for all of the code, you could selectively turn it on and off for targets. Obviously, you have to know you're going to have to know what you're doing here, because as soon as you start using modules anywhere else, if you've turned off the scanning, the build isn't going to work correctly. So the way CMake works, so this is a global variable, CMake CXX scan for modules, and it will initialize the target property on all targets to what you set that global to. And then this is the target property, and it's a Boolean that tells CMake whether to scan for module dependency information. When the set is on, it will scan the sources at build time. And when the property is off, it will not scan them. If it's unset, then the CXX scan for module property is consulted. Note that scanning is only performing if C++ 20 or is hired is on. But scanning for modules, if you have CXX modules and CX module header unit, those are always going to be scanned. So it's just a little extra control over the scanning of modules. Exporting targets. So this creates a file name that maybe include outside of projects, imported from the current project's build tree. So essentially, This is really useful for doing cross-compiling. So not doing like a full install, but instead you want to export into your build tree and then be able to consume that from another build tree. So you might imagine a build like, well, I know VTK has this. There's a wrapping C++ code that wraps the C++ into Python and Java and other languages. And we first have to compile that executable that does the wrapping. And then we can do the wrapping. So if you're cross-compiling, you'd want to do a build tree that built that wrapping tool in the host environment and compile host tool chain, and then you'd have your cross-compile build tree, which would be on the target build, and then you'd want to be able to import those targets. So remember, we want targets to look the same whether they're built or whatever. So we need to be able to import those targets. So this exporting targets. And you can do that now with CXX module directory. Exports module properties to files under the given directory. Each file will be named according to the target's export name. So hey, it sounds kind of cool. You want to try C++ 20 modules out. So using CMake with C++ 20 modules, getting CMake 3.26 or newer, and then read the docs on the experimental to understand how that works, and then get a compiler that works with module scanning, and set up your CMake list file. Right now you still have to do the experimental module API, and then with for the GNU compiler, you still need to include the basically the CMake code that teaches CMake how to use the scan dependencies of that compiler. For Visual Studio and Clang, those are already in the CMake directory because they're actually in releases of compilers. And I imagine this GCC will probably change once it gets completely upstreamed. Whatever it looks like right now probably won't look like that. So, which happens to look like this. You set experimental dynDep on, and then scan deps. And for this, you do the compiler plus defines, includes, flags, -e, -x, C++ source, MT, dynDep files, MD. So F module, TS, fdep file. So a big complicated thing, and that may change. So we didn't want to code it in there that it only worked with some patched version of GCC, and then when the release comes out, it doesn't work with that one. So we're basically just, as long as it's that experimental, if the compiler is still patched, you have to provide this code. Also, if you want to get started on playing around with this yourself, I wrote a blog about this on the Kitwares blog site, Import CMake, C++ 20 modules. And it goes through a lot of this, and I've actually been updating it as time goes on. So I think that'll be the place to go to get set up, and I'll update it as new versions come out as well. Another thing that you can do if you want to play around with it is to look at the test cases in CMake, which are extensive and cover all of that documentation I just went over. You can configure and build. So the way you do that is configure and build CMake from source with module testing enabled. So I run CMake, and I want to turn CMake test module compilation, and I'm telling it I want it to test name, shared partition, internal partitions, export BMI, install BMI. And then I want to give it the compilation rules. And inside the CMake source tree is, so whatever your path to CMake is, there's a .gitlab directory. And underneath that is a CI directory. And under that is a CXX module rules underscore MSVC or Clang or GCC. And that's probably the best way to go because it'll match the version of CMake you're building, and it'll have whatever you need to get the test running. And turn CMake test host CMake on. Experimental module CMake API, you got to get that in there. And then give it the path to your source tree, a path to a binary tree, build it with Ninja, or I guess you could do it with Visual Studio as well. And then you want to run ctest mysr CXX modules, and that's going to run the test suite. And it should look something like this. You can see it's going to run all this stuff, and if you've set it up right, and you've set up your build system right, and you've got the right versions of compilers, all these things should pass. I would definitely recommend doing this first if you really want to play around with this, just to make sure you've got everything working and that the system's working. If any of this stuff fails, then go back to the blogs, go back to whatever, and try to figure out what's going on. And then the next place I would say is to look at the module examples underneath there. So in addition to the unit test, there's under CXX modules, there's an examples tree. And inside there's these list of examples. So there's a simple one, just a very simple main and an importable. There's a circular one. This is meant to fail. It's got something A imports B and B imports A. And this causes an error and gets detected when you try to run the build. It's got a deep chain where it's got a library A, B, C, D, E, or E imports D, D imports C, B imports all the way up. Duplicate, so this one's interesting. It uses a -D flag in a module, so it's got the same source, but it actually produces different, essentially a different module. But the module name, they're in separate targets. It's perfectly legal C++, but the module name would be the same in handling the BMIs across there. We've got an export BMI and interface build, which exports from the build tree using export. Sorry, that thing I talked about with doing cross-compiling. BMI and interface install, which does installing the BMI and the MIU, which is a module interface unit, essentially the source code. Because remember, if you went to Daniel's talk, if the BMI file may or may not be useful, depending on the flags you're using, it may need to be recompiled. So not only do you have to export for install the BMI file, you also have to usually bring along the source for that so that if needed, you could regenerate the BMI file.
I expect it's going to be very common that the BMI is not going to be useful. So you're definitely going to want that. Right?
Yeah.
Or maybe consider it optional. Yeah. Go ahead.
Yeah, there's a generated file, uses configure file to generate the importable module file. We're testing the internal partitions, the library and executable partitions. But anyways, this is a great place to go and see what's implemented in CMake and to play around with it yourself and really to get a handle on it. I would recommend walking through these examples. So running the examples, in addition to doing that CMake minus test thing, which is a bit opaque, I think, to really getting your hands dirty and understanding it. So I came up with this way of essentially configuring them as standalone projects. And it's kind of cool. So you basically, I just created like a CMake source, which gives the path to my source tree. I always use a space in the path when I'm testing with CMake, because yeah, just because I don't want to break something. So that's it's part of our CI stuff. It's part of my culture. It's a big pain in the ass all the time, like command line completion and stuff. Some versions of Bash like add the slash, and then you add something else. You hit tab complete, and it like doubles the backslashes and messes it all up. I don't know. But I torture myself with this just to make sure I don't break anything with spaces in the paths. Anyway, so just anywhere on your disk, you create a random build directory, and then I run CMake -d CMake test module compilation rules. Remember we talked about that? And then you point at inside your CMake source tree at your .gitlab CI, CXX module rules, match your compiler. Don't just copy what I have here unless you're using MFVC. But all the supported ones are going to be there. Give yourself the Ninja if that's what you're using. And then just give the CMake source and then go to test, run CMake, CXX modules, examples, like internal partitions. So take one of the examples and just essentially give that as your source tree. You've made a build tree, and now you don't have to, you're not touching the CMake directory, but you can go in there and do this build. So let's take a look at one. The examples themselves. So if I look in, this is simple, and I just do an ls here. There's a CMake list file. There's an importable.cxx, and there's a main.cxx. Actually, there's a B there, which is a directory I did for a build. But that wouldn't be there in yours. It would just be a CMake list, and then a couple files. If we look at the CMake list is in there, we've got CMake minimum required 3.24, CXX module simple, and then we do this include of the CXX module rules. That's the thing that basically turns on the experimental thing, and it would have that GCC thing in there. And once this whole experimental stuff goes away and we move to production, basically that line's going to just disappear, and we'll just have it regular CMake code. So our add executable target source is simple, private main.cxx, private. We're giving base strs current source directory and portable CXX. We're saying we want CXX standard 20, and then we're adding a test, simple, which just runs the command. So it's what I'm saying is, even though it's test code, these examples are very human readable and worth looking at, and basically a great way to understand what's the state of the art in C++ modules and CMake. And so I can go here. I'm doing a simple running through the whole thing. I run my CMake, and it detects the compiler, says build files have been written. And then I can run Ninja -v, and then we can see it doing its Clang scan depths on the files, and then doing the collation step, and then actually doing the build. So if we look at a slightly more complicated one, this is the CXX modules, export BMI and interfaces. We're just creating a simple static library, and then we're using target sources to give it. We got a private forward.cxx, and then a file set that has the CXX modules. We're giving a base dir, which is the current source directory, and then the private.cxx. And then we've got a public one with importable.cxx. So this private module would be used for building this library, but it wouldn't be something that would be exported outside of it. And then we're telling it that we want CXX standard 20. And then we're doing an install target. We install that target. We export CXX module, file set modules destination, lib CXX MIU. So that's where our module interface unit or the source code would be. And then we're saying our CXX modules BMI destination is lib CXX BMI. And over here, we're doing an install export of the lib export, basically creating the CMake importable target. And we're giving a CXX modules directory, and then writing out the config.cmake. Basically, we're creating that file. This is a new command, which includes the current lister.cmake file. And then we're installing that file we just wrote as well into the lib CMake export file. So if we go in and do Ninja install on this one, you can see that it installs over here. We got BMI importable.pcm, so that's our BMI file. And then our MIU file is importable.cxx. And then we've got the CMake interface target.cmake, and that's the file we would include to import it from another project. And we've installed everything here, CXX module, no config. Cut site. So essentially, this shows the install thing and how it works. Or, as Brett showed me, you can actually go to the compiler explorer, and if you set the right version of CMake, which we were able to get updated, and then the Clang 16, you can actually, here's just a simple one, and then you can see the build worked here. Inside CMake, we've got, I wrote a blog a long time ago about static checks. Things like clang tidy include what you use, CppNow. And the way these work is they essentially ride along with the compiler. What I mean by that is, they run like the compiler, and then they run the static analyzer on the file. And that way, it works with generated files in the build system, and in the case of modules, the module, it would run in the right order of the module dependencies. The restriction is, the compiler would, if you want to consume those BMIs, it would have to be the same exact tool chain. So that might be pretty limiting. And we're also working on exporting a JSON file, but you'd still have to do your entire build and then collect up the JSON file information to do static analysis, because you're going to have all the BMIs already existing.
For current non-modular code, you don't have to worry about patching Clang versions, right?
Right.
But now that with modular code, because the BMIs are sensitive to even compiler versions, they have to match, right?
In theory, we don't know. I mean, we don't know how sensitive they're going to be.
You can try it. Don't be optimistic. Question.
Yeah.
So it sounds like in the general case, once we have GCC with modules, and we're going to have to compile twice to run the static analysis side. We're going to have to run Clang's compile to get the BMIs to feed into Clang tidy, even if I'm using GCC to build the production.os.
I suspect that the ride along that CMake does is just not going to be viable in that case. Because you're going to have to essentially get all the metadata and create an entirely new build plan for your static analyzer.
Yeah.
I think in the worst case that's true, but possibly if you write portable enough modules and you pay attention to it. Like if you have it all wired up in CI, and your CI breaks, if you did anything that made your dependency scanning non-portable across the tool chains, it would probably trip on that. But yeah, there'd be definitely some edge cases around. Like, oh, well, you're scanning slightly different on Clang versus GCC, and so your build got's different or something. But this is developing technology.
Yes.
But like even then, like the module map files are new, so the file commands are going to be different. So there's a lot of deciding that will be tracked.
Yeah, probably. I think maybe CMake can help with this, but I think probably we need some good research and papers from people on about how to help tools interop in this way better. Like how do compilers and static analyzers work together to like coordinate these things. That's part of what it's early discussion and research between Bloomberg and Kitware, but it's like maybe we could have something like a compile commands JSON kind of metadata, but about project structures and dependencies, such that like you could kind of have a portable export of these like module map type information and that sort of thing. I expect we're going to want that sooner rather than later.
building the interface is a lot cheaper than a full compile, so maybe it is just, you have to build a few different interfaces to import into different parts of your downstream tool chains. But you only have to do that for the interfaces, not for everything.
But overall, the build times are gonna drop like a rock once you have modules.
Maybe.
Yeah.
That's still to be determined.
We have good answers, good results from import stood already. The import stood apparently is, at least for MSVC, is faster than including IO stream. So you get the whole library in the time that you were getting just one header before.
Yeah, it remains to be seen, like depending on how you've set up your project and what your trees look like, it may or may not.
I just, as I said yesterday, the pruning of the entities in the BMI, which I don't think anyone is doing yet, is going to be crucial to have that performance. But right now, if you have like several modules and import several modules and there's a lot of overlap, you end up with a lot of duplication of the same entities everywhere. And so the compiler actually has to go and like clean that up. So the pruning of the entities when producing the BMI is going to be fundamental for that performance to actually work.
Clang is chaining. So if you build BCH with Clang, which imports another one, it's actually putting a link. And back in 2020, GCC used to always just grow the output file, but Clang implemented like dynamic lookup into another file.
No, but that's not what I mean. What I mean is when you have when you translate the header, the module interface unit, there's going to be a lot of things that are not reachable from the exported entities. And all of those things are going to be in the module. And if this module import includes headers, and a different module includes the same headers, even if nothing from those headers gets exported, it's still in the BMI, and the compiler has to duplicate them.
Okay.
So the pruning that I'm talking about is from the entities that are exported, pruning anything that is not reachable from the exported entities.
So there's another paper Daniel's got up. For better observability, the output of this tool should store a file name module config.json in the same location where compile.json is currently saved. We did an experimental implementation of this. It's on our GitLab under Kyle Edwards tool, but we're working on this, and this would be something you would use for those analyzers. So what are the next steps? Header units. If you see Daniel's talk, hopefully never. Or something's got to change. So even doing like import std, we might have to redo the BMI on that. So CMake, we are going to add some support to handle things like that, but actually doing like I could see it working well for like the standard library and stuff, but inside a source tree, I think you're much better off just going straight to named modules, putting the small wrapper around the header files instead of trying to like because it's not going to magically turn your include files into importable modules. It's going to cause all kinds of problems and probably cause you to have to change your code anyways, in which case you should just go straight to named modules. We're going to, okay, so one thing, you're probably watching this talk and you're like, wow, that's great. It exports those CMake files, exports the BMIs and the MIUs, but right now there's no way to consume that on the CMake side. We're just generating those files and they're fairly useless. You can't actually find that package. You'd find package include, it wouldn't do the right thing right now. It just would ignore that the BMI stuff. So that's something we need to work on, and we're we should be working on in the next 6 months. I think I agree with Daniel that, by the end of this year, we should be production ready for doing named modules in CMake. And adding the ability to discover and consume modules from other build systems or other packaging systems. And then we need to add this BMI compatibility checks need to be added, and we need to do some research on what that means and actually do some experiments. Mostly they've just been sort of thought experiments now. But again, it's probably going to require help from the compiler. I don't know. One crazy idea I had was, maybe try to give a BMI to a compiler and see if it squawks, and if it does, then you have to do the import. That might work well for, finding external ones. Probably wouldn't work well like inside the same build tree. You wouldn't want to be testing that all the time, but I could probably today write some sort of try compile thing that looked at a module, tried to pass it into the compiler, and if it said black, that BMI is bad, great. I'll fall back to generating my own. I could see that working in some cases without having to do hashes on the compile line and breaking up. That kind of scares me, sort of boiling a compile line down to the essentials and stripping out stuff that isn't needed. I'm wary of how that all is going to happen. I mean, it's complicated enough to create a compile line, much less deconstruct it.
Or like how confident we are that the compiler would return success even if it wasn't slightly matching or something.
Yeah.
And like the white space is not what I meant. Like the BMI might be like look compatible with compiler, but it didn't give you the error code specifically or something. Right? Even though like in the worst case scenario that can end up in like undefined behavior and things like that. Anyway.
Okay, so the status as we are right now, we've got the scanning in Visual Studio 2022 and in Clang 16. There's a patch for GCC. 3.26 or newer has experimental support, and the experimental, we expect to go switch off the experimental and get rid of this experimental API flag as soon as GCC releases a compiler that actually supports this. I think that'll be, we just want to make sure that nothing's going to need to be changed in the API. We don't want to have to support something or have some crazy case where it starts failing for people. Yeah, sure.
Why can't you just release it for Clang 16 or MVC and during CMake that you're using GCC and put up an error you cannot use more?
Well, so the concern is something, it's getting less and less likely, but the concern is that API, that file set API might change because of something GCC does. So early on, like when we did this, certainly it changed as Microsoft compiler changed. The first implementation of this, we had a whole separate thing for module partitions. So the API actually did change, the CMake API, because of the compiler. I think at this point it's very unlikely, but we're still sort of holding out. If GCC changed something that required us to add some extra something to the API, we don't want to have to.
The API is simplified. Like like what Bill was saying in the slides, he worked with Microsoft to make sure you didn't have to put more extra annotations in your CMake to it for Microsoft tools you work. Right? And Microsoft is responsive, and credit to them for that. We can't promise that GCC would have the same outcomes. Hopefully they would, but Bill's saying let's be conservative.
And when are they planning to release the models in GCC?
There's a pull request, and we had some other work going on, and it kind of got paused for non-technical reasons. But we're back on track. There is a patch. It's got some comments on it, and Ben's actually actively working on cleaning up it broke a few tests in GCC. Something to do with the Unicode, but I don't know. Yeah, sure.
Does it need to be a major release of GCC or a minor version would be fine? Because if it's a major release, I think it would be
I think any release, yeah, as long as it gets into a release.
Okay, because if it's a major release, I think it would be April next year.
Yeah, no, we,
GCC 14.
It seems like a big release. It's gonna be a major one.
To be clear, like this is like the import part in GCC works now. The translation of the BMI works now. The only thing that doesn't work in the head of GCC and like from in the latest releases of GCC is the scan dependencies part. So even if we get it in like the head of GCC, I personally will advocate for us to backport this because it's essentially like modules is useless in GCC 10, even though it could work without the dependency scans.
yeah, that would be ideal if we could get it backported. And it's not going to be a huge change. So, yeah, looks like I'm done a little bit early. We can have more time for questions. Special thanks to Brett Brown, Daniel Russo, and Bloomberg for helping make all this happen. Certainly 3-4 years ago when Ben Bakel started coming back to Kitware saying, oh my God, they're adding Fortran modules to C++, what are we going to do? Like, this is going to be a lot of work. I'm like, well, you know, we've already got it for Fortran. How much work could it be? You know, putting on my pointy-haired boss thing. And he's like, it's going to be a lot of work. Like, you're really going to have to fix this. I'm like, how am I going to do that? And then it's tough, too, because, you know, I really, you know, applaud Bloomberg for forward thinking, because the problem is if you go to, you know, if I go to like my national labs customers, I'm like, hey, I want to add modules, C++ 20 modules to CMake, you know, and they're going to maybe make your compiles faster or make your code a little bit cleaner 5 years from now. Can I have, you know, an FTE's worth of work for a year to get that done for you guys? They're like, no. You know, so someone had to step forward and help get this done, you know, and I think Brett's been a huge champion, and obviously Daniel's really dug into the technical side of it, and really helped root out the conundrums that were in the specs and actually make this something that was implementable. So I'm excited, and I think it's going to get there, and it's been a long, slow ride, but I think we'll end up somewhere that's good when we're there. Are there any other questions? Okay. Thank you.